Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this discussion, which is second part of our spatial interpolation techniques. So, in the first part we have discussed the interpolation up to the linear one. Linear interpolations are not that popular, but sometimes for certain requirements one can definitely go for linear interpolations. Those options are available in the softwares, and one can go for even for Thyssen polygon. One can create Thyssen polygon, but it is a old method when we did not have these GIS softwares or any such softwares. Then it was people were only resorting to Thyssen polygon. Anyway, now we come to this other type of interpolation techniques, which is being considered as non-linear, which is again based on the Tobler's law of geography, and which says that points close together in space are more likely to have similar values than points farther apart. And using this concept of Tobler's law of geography, there are interpolation techniques which have been developed, which are based on the distance weighted interpolation techniques. So, if for an unsampled site interpolation has to be done, then the point which is among input points, the point which is closest will have the highest weightage, and the point which is having further will have less weightage, and this is what is called distance weightage interpolation. Exact interpolation in that way is IDW, which is inverse distance weightage interpolation method, in which the points which are very far for the estimation for the cell which is going to be estimated, then their weightage will be less. So, this interpolation estimates cell values, because we are after all going to create a raster by averaging the values of the sample data points in the neighborhood of each processing cell. And as per Tobler's law of geography, that closer a point to the center of the cell being estimated, the more influence or weight it will have in averaging process. Now, for example, if I take this schematic which is showing a terrain and some input points, and also showing a search radius in a form of circle. So, points for this unknown point which is in the center, whatever these red dots are there, red small points are there, the point which is very close will have the maximum influence while determining the value for that one, and point which is very far like this one will have the less influence. Now, we can fix this search radius also. So, we can fix either by number of points for this kind of search and estimating the value, or maybe a radius for a circle. Now, so IDW interpolator assumes that the variable being mapped like here in this figure, it decreases in influence with distance from its sample location. That is why it is called inverse distance weightage. And for example, when interpolating a surface of pollution, as we know that a more distant location will have less influence of a pollutant. So, if a chimney is emitting certain pollutants, if you away away from that, it would be less concentration of that pollutant. But if you want to do such a prediction about this pollution which is getting dispersed in the 3D space or in the air or in the atmosphere, then for realistic prediction you require not only the location of that chimney in geographic space, but you also require the wind direction and wind speed as well. or any other impedance. There might be some tall trees or other things. So, they may again create. So, if you want to create a real good prediction about such plumes, then the best thing is, as best inputs you can provide, better the interpolated surface is going to be. Now, for linear examples, as we have seen that first if it is falling, whichever the point is close will have the maximum influence. If I take a little different example here for this unknown location where question mark is there, and these are my input information which I am having, and these are the distances which are marked as like 40, 20, 100 and 200, and these are my points are these A, B, C, D. Now, for this unknown location I want to predict. That means in this nonlinear interpolation techniques, or especially in this IDW technique, inverse distance weightage technique, the point point which is having the minimum distance, the point A is having minimum distance to unknown location, will carry the maximum weight while calculating the value for this unknown location. So, what in IDW, what is the first step? That distance from each neighboring point is measured, like here in this schematic it has been shown. Now, number of points to include in the search can be selected either in form of number of points or in form of a radius of a circle. We will see some examples also. Then the distance is calculated according to the formula. And what is that, how these options are available? So, this is example from ArcMap, ArcView GIS. These are green dots are my input points. If I choose this inverse distance weightage method, then what I am seeing, and the Z value I am taking here as a pH value, and I am providing power and other things which are different options are available. Search radius I am saying variable, and it should search minimum 12 points around my unknown location for that cell. And there are further details are there, and I can also control spatial resolution of my data. And if I am having prior knowledge about the terrain or of that area, then I should also provide the barrier information which will bring abruptness in my data, and that would be more close surface representation than a surface representation without barriers. So, if we want to create more realistic surface, all these informations, especially about the barriers, is very much required. Now, when we say about the power, what does it mean by power here in this particular method? So, power basically means that it controls the significance of known points on the interpolated values. So, you provide high power, instead of say 2, you provide 4. That means the input point will have more weightage while determining point in the surrounding for unknown location. So, this based on their distances. Of course, this is inverse distance. So, everything is decided based on the distance. Closer the less the distance, more the influence from the output point. Now, when we provide higher power, means emphasis is placed on the nearest points. When we provide low power, it will give more influence to the points that are farther away, and that means more smoothened surface. But in case of high power, we get less smoothened surface, though the overall technique is inverse distance. So, a power of 2 is most commonly used, and that is why it has been kept in default here with IDW, and therefore, it is default here. Now, further if we go for this search radius value, here what we have in this example we have kept as variable, but when we keep a variable or there are some other options are available. So, this characteristics of the interpolated surface can be controlled by applying a fixed or variable search. So, we can choose 2 options which limits the number of input points that can be used for calculating each interpolated cell. So, here in this example I kept variable, but if I fixed, then only those number of points in the neighborhood would be searched. So, again here if I want more smoothened surface, then I will go for variable, but if I want more rigid surface and less smoothened surface, then I will go for fixed radius. So, less number of points for each cell calculation to improve processing speeds. Of course, if the search for less number of point is involved, then the processing time would be less. Otherwise, the software point of view, they have kept value 12 as a default value. One can also limit the number of points far from the cell location where prediction is being made have no spatial correlation. That means the points, if they are very far, though we may keep a large number, but as you know that they should not have any influence or should not have any influence on for that cell for which we are determining the value. So, always there has to be optimum number of points or size of the radius which we choose. Considering very far points, basically you are creating a predicted surface which may be very far away from the real situation or reality. So, one has to be very careful while choosing these options. Now, next is the barriers. Barriers part we have already discussed little bit, but anyway it is a polyline data set. It is not a point. Barrier always has to be a polyline input file based on the break line, also called break line, which limits the search for input sample points. Basically, during the interpolation, if you have provided a polyline theme which is representing say a geological fault, then beyond that line no search would be made. And this polyline, as we know, that can represent in topography a cliff, a ridge or some other interruptions of a landscape. Even a stream in case of groundwater or surface water can be considered as a break line, and only those point samples on the same side of the barrier as the current processing cell will be considered. So, this controls your surface, and when you create a surface using barrier lines and you are having prior knowledge about that, then your surface would be more real one, more close to the reality than without using barrier lines. So, in any application if you are using such surfaces, whether for groundwater, hydrology or pollution or any other thing, if you are having that information, bring that information in form of polyline theme and provide that input, and you can create a very good more realistic surface. This is how it influences the break line. If I provide the barrier information, then this is how my surface in 3D would look. And with this without barrier, this would be a more or less quite a smooth surface. So, it is more real, more close to reality than this one. If there in nature, in a topography, there might be a vertical cliff like this, and if I am not using barrier, I would be predicting the surface like this, which is grossly inaccurate. So, in order to have better accuracy of our surface, it is always, if possible, provide the barrier information while doing the interpolation. So, from geological point of view or from civil engineering point of view, fault lines, cliffs, streams and other features which can be which are discontinuous lines, polylines, and which controls how the surfaces are generated. Now, there are various interpolation techniques. So, IDW and kriging will support the barriers. Like if somebody is trying to use barriers in case of linear interpolation like Thyssen polygon, then it is not possible, because Thyssen polygon by its characteristics itself is a abrupt interpolator, and therefore such options will not be there in the softwares either, because theoretically it does not fit there. Now, about the search radius. So, if we provide the number of points that search 12 surrounding points or 5 surrounding points to determine the cell value of this grid, then it will do the search up to the number of points. But if I provide a fixed radius, then it will search based on the radius rather than number of points. So, both options are available. And now this characteristics about the search radius is an interpolated surface can be controlled by limiting the input points used. Points can be limited specifying the maximum number of points, which will select nearest points until that maximum number of point is reached. Alternatively, a radius can be specified in map units also, as you can see in the bottom figure. So, both options are there. For example, here the type, which type of your interpolation is. So, this search radius can be controlled either with the maximum number or giving a search radius. Now, there are some other parameters which are also considered, and if I go for another type of interpolation technique which is called Spatial. Of course, this also falls in the category of nonlinear interpolator. Here we are taking the same input layer of points. Now, here the options would be little different because it is a different interpolation technique. So, first option is about this which type of spline, because as I mentioned earlier that each interpolation technique, especially these non-interpolation techniques, will have their own variant also. Now, which is most suitable for your data set is a very difficult question that we will be discussing later. But for time being, if I say that I am going to use spline instead of IDW interpolator, then there are various spline. So, first if I say two types, one is the regularized, another one is tension. So, two options would be available. So, if I choose the regularized method, which creates a smooth gradually changing surface values that maybe lie outside the sample data range. So, regularized option in spline will create a very smooth surface relatively compared to the tension method, which controls the stiffness or abruptness of the surface according to the character method of modal phenomena, whatever, whether say elevation or concentration of any other parameter. And it will create of course less smooth surface as compared to regularized with values more closely constrained by the sample data range. So, each, that means the each interpolation method, whether it is a IDW or spline or kriging, which we will be discussing, all will have their own variants. And while choosing these variants, one should fully understand what they are there and what are in the defaults. Because the software people may put something in default, but that may not suit for your data set. So, one has to be very careful while choosing. Now, this spline interpolation method based on a concept which is called French curves, say old technique, when we did not have basically the digital techniques, then at that time people used to have these French curves. Still you might see that these tailors, when they cut a cloth to fit a pant or trouser for a person, they use these curved scales. You might have observed that one, or while preparing a coat they use the curved scale to bring that curvature in the cloth so that it fits very well with the body of a person. Same concept here about this French curves. So, in spline method estimates the values using a mathematical function that minimizes overall surface curvature, resulting in a smooth surface that passes exactly through the input points. Like here, these are the examples of French curves. Earlier architect, when they did not have the softwares, or civil engineers, they used to employ these French curves. These used to made of acrylic sheets or wooden sheets, So, here what this is doing as spline, that it is minimizing overall surface curvature, and what it is doing, creating a smooth surface. Here we are seeing in 2D, but this is how the smooth surface can be created like this also here. Now, if one would like to learn what is mathematics behind against these all methods and their variations or variant, then all that is available in standard softwares or elsewhere in the literature. For example, if I choose the linear spline interpolation, then this is the mathematics which is involved there. If I go for other options like quadratic spline or cubic spline interpolation, I am having a complete mathematical background available to understand or to develop further. Many of such options may not have been implemented today. So, we can further develop individual interpolation techniques to suit our data sets. Now, there is other regularize and this tension method and tension apply we have just discussed. So, we will go for the next interpolation technique which is called kriging. Very popular, and when we did not have the proper GIS softwares, we used to resort to a software which is called Surfer, and this Surfer is very powerful and very good for kriging interpolation. But now GIS softwares are also capable of producing raster surface using kriging, and their variants versions of these kriging are also available. So, basically kriging is a geostatistical technique which is a group of geostatistical technique. That means various variants of kriging are available to interpolate the value for the random field or for unknown location, and that value can be a elevation value like Z value of the landscape as a function of geographic location at that unknown location at an unobserved location from whatever the observations which we are having in the nearby locations. So, it is more or less in the same way as other interpolation techniques, but it is based on the completely on geostatistical techniques, and there are certain advantages with kriging interpolation which we will also see. So, what theory says that the interpolation and extrapolation by kriging, which was developed by a French mathematician whose name was Georges Mithron, based on the master thesis of Daniel Craig. So, this the term kriging is coming from a master thesis, and it was a really great contribution in the field of mathematics, especially in geostatistical techniques and spatial interpolation. Now, kriging, if you recall that we had different kind of categories or different way of classifying different interpolation technique. So, in that sense the kriging is stochastic, and which is incorporates the randomness in it, and in nature many things many surfaces may have that phenomena, and also it is exact, smooth or abrupt depending on what choice we go, and global or local, those options would be available. So, smooth and abrupt option would be available and global and local would be available. But these exact is very important here. That is why a lot of people prefer, so that it provides both exact, smooth or abrupt, global or local, and is a very good. Plus it also estimates the error. For other interpolation techniques, it is not possible easily to estimate errors, but in case of kriging it is possible. This is what this figure is depicting, that the interpolated surface is shown in the red curves or red lines, and then you are having input points, and of course this is a 2D or in linear or 1D representation like this, and not really as a surface, but in a linear fashion. So, these are the observations in blue boxes, but if I keep a 95% confidence interval, then there may be a surface which is going like this, kriging surface, or there may be a surface, though they are exactly passing through our observation points. That is why it is exact. Same time it is smooth as well. So that between these 2 points it is following some smooth path. So it is smooth. If we can constrain this one, then it can also become abrupt. And if we change the radius or other parameters, then it can become either global or local. So kriging is a quite powerful interpolation techniques. So as you know that natural data may be elevation or any other characteristics of nature data which are difficult to model using smooth functions, because nature may not be like that only. So because normally random fluctuations exist, especially the terrain like Himalaya. I have given examples. If I am predicting a surface for terrain representation, then I cannot go for a smooth surface. It is a random fluctuations, and measurement errors will combine to cause irregularities in the sample data values. So chances of errors are much more in case of if this is not random fluctuations are there, and therefore we have to be very careful about this. Since kriging has been developed, as we have discussed, as based on the stochastic concept, and it is a regionalized variable. It is based on the concept of regionalized variable, and which has got 3 components. The first one is the of course your data is there, like here the data is shown in these dots. So the first component is the structural one, which is shown in the red line in this diagram. So this is a structural component of kriging surface, which is completely a straight line, or you can say linear. So this may be represented by a mean or a constant trend. So a structural component is a linear kind of thing, whereas a spatially correlated component, which is represented in this diagram as a green line, which you are seeing as a thick green line like this. And the third one is the random noise. Now this random noise is errors, and this is what the advantage, that it can also predict errors by it when you go or resort to the interpolations. So we can separate out all 3 components or key components of kriging. One is structural, spatially correlated, and random noise. So we continue with this, that earlier figure we can separate out as a 3 components. So that the first one is the structural component, which as I have mentioned is a linear trend, linear one. This is a spatially correlated component, and last one is the random noise component, which is non-fitted in that sense. So kriging is implemented using a semi-variogram, and there are many different varieties of kriging, means variant of kriging exist, and many of such variants have also been implemented in many GIS software. Selecting which the appropriate one, which one is the most suitable for my input data set, is maybe sometimes very challenging, and therefore it requires a careful consideration of the data. And if we are having prior knowledge of the terrain conditions or characteristics of my input data points, then I can choose a, otherwise no literature or no software will ever let you know that choose this variant of the kriging or these options within the kriging. No, nobody will ever tell you. So it depends on your data type or data input or characteristics. Now if I take example, though it is a little older version of example, but does not matter, even in latest version of ArcGIS, almost same options are available. So here I am taking a input which is a soil sample data, and I may take a value here, say pH value. Currently it is just displaying a other value. Now 2 kriging methods, variants are there, either ordinary kriging or universal kriging. And as you name implies, universal will create more smoothened surface, and if we go for ordinal, it will create a more local fitting surface. Now, semi-variogram models can be various options, spherical or circular or many other. And then of course, the search radius type, which we have discussed in other interpolation techniques almost the same way, variable or fixed, two options would be there. And of course, when you are creating a raster surface from input point data, you can always control spatial resolution. By default, it may give some, but may not be acceptable to you, and then rest of the things you provide where to be stored and other things. So, basically let us devote some time about the what is this semi-variogram. So, semi-variogram is based on the modeling, and that is the squared differences in the z values as a function of the distance between all known points. So, based on this input, semi-variograms are modeled. Now, mathematically basically that becomes as per this equation, and as we go from the distance, this becomes quite flattened. So, that is Taubeler's law of geography. And if we see a further example on this variogram or semi-variogram produced using say this geostatistical analyst of ArcGIS, then here what we are getting a semi-variogram like this against these input points. You can also calculate other parameters which may be required to better understand the generated surface for that purpose. Now, one of the very useful outputs from Kriging analysis is that error part or uncertainty surface that we can generate, and this basically will answer how good the predictions are or how good the surface which you have created, which is more close to the reality. So, there are though there are various techniques like IDW, Spline, Kriging and their variations or Thyssen Poly, but except this technique Kriging, no other technique will let you know that what is uncertainty factor. So, that is why many people resort to the Kriging, and one can create an ordinary Kriging map and a map showing standard error of predictions, and you can compare with the 10 also. Now, here using the same input points, 3 surfaces have been created using the 3 nonlinear interpolation techniques which we have just discussed. So, first one we discussed the IDW technique, and the option we chosen is moving average, and this is how the surface, though this surface is shown as a 3D surface, does not matter. So, here this is how the surface will look. But if I choose the spline and the option is moving surface, see the moving average, moving surface, different concept. So, if I use this option in spline, this is how my surface is going to be created. Remember that input point is the input point theme is the same for all 3 surfaces. And lastly is the Kriging. If I create a Kriging surface using the same data points, this is how the surface would be created. Now, which one is more close to the reality, that has to be assessed. In case of Kriging, uncertainty information would be available, but in case of IDW, that information is not available to us. Now, there are various options like here natural neighbors. Then you can create a trend surface, and if I say draw a cross section or a profile for all 3 surfaces which we have just discussed, then and the input points are also shown here as blue dots. What you are seeing that this this blue one is the Kriging surface, which is having more variations, but sometimes it is very well fitted between these 2 points. But in case of spline, as you can see, this yellow one is a exact fit. So, it is going and touching all input points, whereas IDW is going in between points, not exact in this particular example. Because all these interpolation while doing these through these softwares, you are having different options So, if you do this, you may get various surfaces, and you have to be very careful while choosing which is the best for your input data set. So, this is the problem about the accuracy. Which surface or which interpolation is more accurate for my input data set is a very difficult or challenging, but it is possible to assess to some extent. Visual representations can be compared if you are already having that some knowledge, prior knowledge. Another problem will come about the edge effects, that is the lack of data at the margin or extent of the input data points. You do not have any input points, and that means it would be doing extrapolation. So, there might be some edge effects in the data. The best solution is you define a large extent initially, and later on you can extract for a smaller area, and that will reduce your edge effects. And basically this brings to the end of now this discussion. So, this was spatial interpolation techniques we have discussed in 2 parts. This was the last part. Thank you very much.